So today I'm going to be talking about designing gaze visualizations for remote collaboration. So remote collaboration is becoming increasingly common and changing how we work and learn from others. However, these distributed environments often lack many of the rich interpersonal cues that make for effective co-located collaboration, such as information about where your partner is looking. And to address these challenges, we, along with other researchers, have been developing techniques that integrate gaze information into distributed settings, called shared gaze visualizations. And this involves collecting eye movement data from both participants in a pair and displaying information about where one participant is looking to their partner. So you'd be able to see where I'm looking, and I can also see where you're looking. And these are designed to improve our gaze awareness, or the ability for you to understand what I'm attending to in our shared space. And what I'm going to be focusing on for this talk, like many of the other things in the session, is how this can be designed. So how can we represent gaze information for remote collaboration? There are a lot of different ways that you can choose to represent gaze coordinates, and that can change the way that they influence remote collaboration. So for example, you can take a single fixation point like this and directly visualize it. You can do something like a face overlay of your partner, which is going to show you roughly where they're looking in the shared visual space. But there are many different techniques in between. And these different visualization techniques can afford different interpretations. For example, a scan path or a SIGCHI can show how you traverse the visual space, whereas a heat map is going to highlight duration, or where you are fixating the longest. So in these two examples, you can see a scan path on the left and a heat map on the right. And what you'll notice here is that they're both representing different information about the gaze and how someone looked at the visual space. So you can identify a path here on the right, whereas you're going to notice that they spent the most time fixating in the four corners on the left. And when we look in the literature, we see that gaze is most commonly illustrated as a single visual point, so that first example that I showed. But there are some other works looking at different visualization techniques that we're noticing across the bottom. But these different papers typically look at one visualization technique applied to a single task. So we're just creating one new representation and evaluating it in an isolated context, with the exception of some work in competitive gameplay by Noon et al. And some work in the co-located collaboration space by Zhang et al. But in the remote collaboration space, we have yet to make a concerted effort to compare visualization techniques across the same task, so we can understand how the different ways that we represent gaze information can impact collaborative behavior. As we can expect that, like I said before, the different ways that we visualize gaze information can influence what information we're taking away from the visualization, which can be more or less useful depending on the collaborative task. So to begin to understand these factors, we developed and evaluated 3 exploratory gaze visualization techniques for remote collaboration, and each visualization technique was designed to represent a different feature of eye movements. So starting with the heat map visualization, it highlights fixation duration as well as coverage by marking areas where someone has been looking and darkening from yellow to orange the longer that they look in the same region, or if they revisit a same region. The shared area representation displays a circle around an area when a pair are looking at the same thing. So if we're both looking at different areas, you're not going to see anything. The second that our gaze paths overlap, the circle is going to be displayed around that shared area, and it's only going to display as long as we stay together, so as long as our gaze paths remain overlapping. And this is meant to illustrate mutual gaze, or us looking together. And lastly, we have the path visualization, which is illustrating a current fixation point, as well as most recent SIGCHI. So it's connecting a current fixation point with a previous fixation point, which is meant to draw connections between how someone is looking at the visual space, as well as illustrate where they're currently fixating at all times. And we have a no visualization baseline. And to evaluate these different techniques across the same task, we chose a hidden image search task. So this is an example of the task. On the left, you're seeing a hidden image. So it looks like a larger picture of cats reading Joy to the World. And embedded in this image are a bunch of smaller objects, which you're seeing on the right. And so to start with an example, the target object is highlighted in purple. It's a mouse. And to make it a little bit easier for you guys, the mouse is right here. And as you can see, it's designed to hide within the image, so it's not particularly noticeable, and the orientation has changed, which makes this task a little bit challenging. And so for the experiment, we had participants find 3 objects together, and so in that situation, once one of the collaborative partners found the object, they had to explain the location to their partner. So now that you all know where the mouse is, and I knew where it was first, we can now move on to the next object. And we did this for 3 objects. We could not move on until both participants in a pair found it. Following those 3 collaborative searches, pairs did 3 independent searches. So they were both looking for different objects. They did not have to wait for their partner to find their object, and they could move on without them. And participants did these sets of 6 searches, collaborative and independent, for each visualization technique. So this works out to be a 2x4 design with task coupling, collaborative or independent searches, and gaze visualization, which is the path, shared area, heat map, and no visualization baseline. And we counterbalanced the visualizations. And so we conducted an experiment with 48 pairs to understand how these different visualization techniques impacted their coordination and collaborative behavior. And so to look at this, we evaluate outcome measures on performance, process measures on their gaze behavior, as well as surveys and interviews to understand the perceived value of these different visualization techniques. And so as I talk through the results, I'll define each of these measures. So we'll start with outcome measures, which include total collaborative completion time and coordination time. It's important to note for these results, I'm focusing only on the collaborative searches. So when we look at total collaborative completion time, it's the amount of time it took from the start of the search to when the last person in a pair found it. So that moment when both people had identified it is the total collaborative completion time. What we see here is that the heat map visualization is significantly slower from the group mean. So people are slower to find objects when the heat map is displayed in collaborative searches. But when we look at the coordination time, which is the amount of time it took from when your partner found the object to when you then found the object, so that explanation period of defining where the location is, we really see the effect of the gaze visualizations. So we're seeing here the results of a Tukey's HSD test, which is showing that the path and shared area visualizations are significantly faster than no visualization, and heat map lies in the middle of those. And so what we're seeing is that with the gaze visualization, pairs are faster at coordinating on the location of the object together. So we can use the visualization as a resource to help communicate about the location of the object that we're trying to find. And this is consistent with the prior work that suggests that gaze visualizations can be useful as a referential pointer. And to understand this in a little bit more depth, we also look at the process measures, which are going to show how people search the visual space. And this includes quadrant overlap and gaze overlap in time. And for these measures, I will discuss both collaborative and independent searches. So overall quadrant overlap is the fraction of time during which participants looked at the same quadrant as their partner for each object. So in this example, we see high overlap on the left, which is that both the green and the orange participants are searching the same quadrants. So we're not being very effective searchers because we're both looking at the different parts of the image equally. And on the left, we see low quadrant overlap. So here we're noticing that the orange and green pair have successfully divided the visual space. And we have the orange pair focusing primarily on the top and the green participant focusing on the bottom. And so to look at the results, we see the collaborative searches in blue and the independent searches in red. And what you'll notice first off is that the collaborative searches have significantly more gaze overlap than the independent searches. And this makes sense because they are searching for the same object, so at some point they will have to come together in the same quadrant to locate the object. But if we look within the collaborative searches, we see that pairs have significantly more quadrant overlap with the path visualization compared to shared area and none, while heat map lies in the middle, suggesting that when the path visualization is displayed, pairs are more likely to attend to their partner's gaze visualization and look in that quadrant that their partner is looking at. And interestingly, we don't see any effect of gaze visualization on independent searches. So when pairs aren't searching for the same objects, we're not seeing an impact of the gaze visualization, although it was displayed during these independent searches. But that overall measure of quadrant overlap just captures how pairs divided the visual space, but it doesn't tell us if they were looking together in time or establishing joint attention and looking at the same objects together at the same time. So to look at how pairs searched together, we calculated how often they spent looking in the same point at the same time. And so in this example on the left, we have our orange and our green participant, and we're looking at their gaze paths. So they're starting at point 1 and they're ending at point 7, and that's how they're traversing the image. And we see that at points 4, 5, and 7 that they're establishing gaze overlap in time. So they're looking at the same point together. And here we again see the same kind of results where collaborative is in blue and independent is in red. And again, we're seeing significantly more gaze overlap in time with the collaborative searches compared to independent. And this is also expected because they do have to do some coordination to locate the object together. But when we look within the collaborative searches, we see that the shared area visualization has significantly more overlap in time compared to path and none, or compared to heat map and none, while path lies in the middle. And this is an interesting difference from the quadrant overlap, because with the quadrant overlap, we saw less quadrant overlap with shared area, but we're now seeing more overlap in time, right? And so this is suggesting that with the shared area visualization, pairs are able to divide the visual space, but when they need to coordinate together in time, they're able to establish this joint attention and search together. And so they're able to kind of do that balance, where we saw high levels of overlap in time and quadrant overlap for the path visualization, suggesting that they're not doing quite the level of division of labor. And again, we don't see any difference within the independent searches. So this is not impacting how they search together in time, which we would expect because they're not searching for the same objects. And so to understand how participants perceive the visualization techniques to differ, we conducted a survey and a semi-structured interview. And so to look at a subset of the survey questions, we see that the shared area visualization was reported to be highly useful and significantly less distracting than the other two visualizations. So it's kind of this right spot where it's not distracting users from the task, but it is perceived as being useful for the task. In contrast, with the path visualization, we do see it to be perceived equally as useful as the shared area, but significantly more distracting. So while it is useful, it's distracting from the task, which is not what we're trying to achieve. And the heat map visualization is significantly less useful than shared and path, and significantly more distracting than shared. So it's both perceived to be less useful and more distracting. So clearly that's not the best fit for this task as perceived by the users. And this is further reflected in their interviews. So participants reported that they couldn't help but follow the path visualization. It suggests that they're having trouble not attending to that visual representation of their partner's gaze. And this is reflected in the quadrant overlap results that we talked about, where we saw high levels of quadrant overlap with the path visualization. So they're likely to attend to that visualization, whether they're doing it on purpose or not. With the shared area, participants reported that they were able to do their own thing and just target the objects together. And this is definitely reflected in the two types of searching results that we looked at. So we saw the division of labor approach with the shared area visualization, as well as this coordination period with high overlap in time with the shared area. So we're able to support both parts of the task, and participants were aware of that. And as expected, the heat map was reported to be distracting, and the visual occlusion was not helpful for participants. And this is also illustrated in the overall completion time, where we see that participants were on average slower with the heat map visualization, so it was not being an effective supporter of this task. And so to summarize these results, we see that shared area or shared gaze visualizations can support coordination. So this is consistent with prior work that people can use shared gaze visualizations to coordinate on objects and things that they're discussing together. We do see that the task dynamics influence the effect of the shared gaze visualizations. So we did not see an impact of shared gaze visualization technique on the independent searches, but we did in collaborative searches, right? So this relationship between the pair matters. If I associate you as a collaborator, I am going to maybe attend to your visualization more because I know that we're working together. When we're not working together, your visualization is not necessarily distracting me from the task or influencing how I'm going to go about my search. And we see that participants' perceived value of the shared gaze visualization differed based on the technique. So participants did report that some visualization techniques were more useful for this task than others. So they are noticing a difference of how we visualize it that impacts their ability to use it for the task. And this has implications for design, right? So with respect to design, it's important to consider the availability of the visualization technique. So always-on visualizations are always visible to their participants, like the path and the heat map visualization, so they're always displayed, right? And for this task, those were perceived to be distracting because they're always on. But that distracting element might just be because that wasn't a supportive mechanic for this task. We can think about other tasks in which those types of behaviors that were elicited by those visualization techniques could be useful. So the path encouraged following along behavior and supported this coordination, which could be useful for more instructional tasks, where you have an expert explaining something to a novice and they might want them to follow along with their instruction, and therefore that's the behavior that you're trying to achieve. And then the heat map visualization discouraged following behavior and wasn't as useful for coordination. And so this could be more useful for other tasks that require maybe a more of a division labor approach, or as we saw yesterday, there was a talk that discussed real-time heat maps being useful to understand intention in competitive gameplay. And so competitive environments might benefit from this type of visualization, whereas collaborative environments did not necessarily seem to benefit. But what's really interesting is the space for partially available visualization techniques. So the shared area visualization was only displayed when participants were looking together at the same time, but wasn't during the rest of the search, which allowed it to support both division of labor as well as tight coordination, which is kind of the right fit for this task, where you want to be able to search separately, but once you identify the object, you want to be able to explain that location to your partner quickly. And so this partially available space was the right fit for this task, and this is a kind of a new technique for the gaze visualization space. So I think there's a lot to be explored in these partially available techniques that can be designed specifically for the task. And so what I want to take away is that shared gaze visualization design should be informed by the context and task requirements. So in the literature, we see a lot of the same approach being used over and over again, and it seems that in this new wave of research, we should start to think about how the visualization design can be informed by the task to better suit the task needs as well as the participants, so we can create a more effective gaze visualization and stop distracting people from their tasks and support them on working together. And what I want to end with is a lot of these visualization technique examples that I used were designed with our software called Iris, which helps users create their own gaze visualizations with this kind of direct manipulation interface that's fairly creative, and we demoed it here on Monday. And so the code and the software is available for download on our website, as well as the code for this experiment. So if you're interested in doing gaze visualization research, you can look over there for those resources. I'd like to thank my co-author, Darren Gergle, and the undergraduate researchers, Jeff Brewer and Nancy Yao, who supported this project. Thank you.
We have some time for a few questions.
Hi, I really liked your talk. I'm Chris Collins from UOIT. I was wondering about if you considered a kind of hybrid as an implication. So you talked about partially available. I'm thinking like if you did the path visualization as a just noticeable, like really faint, and then switched into the shared area if the person chose to follow it or something like that.
Right, yeah, that's a really interesting question. And there's been some work in called subtle gaze direction, where they show something in the periphery that attracts your attention without perceiving it. So it's a really interesting technique, and I think that would be really cool to explore.
Yeah, it's really fun. I think you've opened up a really good design space. Thanks.
Hi, Joshua Dean, University of Melbourne. So I have a question. So it's so shared gaze awareness in remote settings. It's highly dependent on both users being calibrated. Have you thought of visualizations that would work with full calibration?
Yeah, so that's one of the things that we were talking about with this experiment is we are using kind of low-cost remote eye trackers. The calibration is not as good as highly experimental eye trackers, but these visualization techniques can be robust to that low quality. So the heat map visualization is one that does really well when you don't have a great calibration quality, as well as shared area because it is encompassing a larger area, whereas the path visualization is very vulnerable to these kind of noise in the data. So I do think there's a great space for looking at those kind of visualizations.
All right, thank you.
Thanks.
Hi, Andrew Duhovsky, Clemson. Quick question on the experimental design. Even though it's counterbalanced, the within subjects design here has a potential problem of inducing a learning effect in terms of performance. Did you consider that in your analysis?
Yeah, so we did consider that, and we do counterbalance by gaze visualization technique, which is what we're looking at in the performance results. So that should all work out. But we do see a little bit of learning result over time, but we do consider that in our linear mix model. So it's accounted for.
All right, thank you, Sarah, again. And